This screencast is about residual analysis, that is, checking the simple linear regression model assumptions. The linearity assumption is that x and y values are linearly related. The independence assumption is that the random errors are independent of each other. That is, knowing the most recent random error value will not help better predict the next random error value. The normality assumption is that the random error values are normally distributed. The equal variance assumption is that the random error has the same general tendency to depart from the expected value of y, given x takes on some specific value of x, over the full range of possible values of x. The equal variance assumption is also referred to as homoscedasticity. The acronym LINE may aid in remembering the model assumptions. L for linearity, I for independence, N for normality, and E for equal variance. The residual values EI are used as proxies to the model's random error quantities epsilon I for the purpose of checking the model assumptions. When checking the model assumptions, two plots are always required. A third plot is required only when the data is collected in a time sequence. The two required plots are: the first is a scatter plot of the residual values versus the x values. The other required plot is something called a normal probability plot of the residual values. We will discuss creating a normal probability plot on the next page. The third plot, number 2 here, is a time series plot of the residual values, and as I said, that's required only when the data is collected in a time sequence. We will discuss these plots in more detail. Linearity or fit, or lack of it, can be observed in either a scatter plot of the x values versus the y values, or a scatter plot of the x values versus the residual values. The lack of linearity is easier to see in the scatter plot of x values versus the residual values, and this is the required plot. The plot on the upper left is a plot of the y data values versus the x data values. The plot on the lower left is a plot of the regression residual values versus the data x values. We can see curvature in both plots. The required plot, however, is the residuals versus the x values. It is easier to see this curvature, especially in close calls, in the plot of the residuals versus the x values. For the data on the left, the linearity assumption is not satisfied, and this data is inappropriate for a simple linear regression model. The plots on the right are for a different data set. The plot of the y values versus the x values shows no curvature. The plot of the residual values versus the x values shows random scatter, that is, no curvature. These plots on the right indicate data appropriate for a simple linear regression model. Again, it's the plot of the regression residual values versus the x values that's the required plot. A check of the independence assumption is required only in the special case of data that's collected over time. When data is collected over time, we'll assume the time order is reflected in the index values I equals 1 through n. When data is collected over time, a plot of the regression residual values versus the time order is required. Additionally, when data is collected in a time order, a hypothesis test for positive autocorrelation is also required. This hypothesis test will be discussed in the next section. A scatter plot of the regression residuals versus the time order, showing only random scatter, provides evidence that the independence assumption is satisfied. To check the normality model assumption requires viewing a normal probability plot of the regression residuals. An NPP that resembles a straight line indicates that the normal assumption is satisfied. This NPP sufficiently resembles a straight line to indicate the normal assumption is satisfied. Details on creating a NPP appear on the next page. The equivariance assumption can be checked by viewing a plot of y values versus x values, or by viewing a plot of the regression residual values versus x values. These are the same plots used to check the linearity assumption. Again, equivariance, or the lack of it, is easiest to see in the plot of regression residuals versus x values, and this plot is the required plot. The two plots on the left show a situation where equivariance does not hold. It's easiest to see that the equivariance does not hold in the plot of the regression residuals versus the x values. In this plot, we see an increasing cone shape as x increases. The plots on the right show a situation where equivariance holds. One caveat, however, is that where dots are dense, it's okay for there to be more spread. That's natural. You should read this next page on creating a normal probability plot. You will be required to create a normal probability plot on the homework. The next 4 pages is a residual analysis for a specific problem described here. You should go over this problem.